All right, so let's do an example. So I'm going to set up this problem, and then we're going to draw the free body diagram, and then use the free body diagram in Newton's second law. All right, so let's say that there is a 10 kilogram mass. And it's hanging from two cables connected to the walls. This location is -2, 1. This location is +2, 1. The origin is the center of mass of the mass. And we want to know what are the cable tensions. Okay, so we're going to use Newton's second law to calculate the cable tension. That means we have to draw a free body diagram. And to draw a free body diagram, you have to choose something to isolate first. Often it's not, this isn't like an ironclad rule, but usually you're going to have to include the weight of an object in your calculation, and therefore the problem has to give you the mass of the object to calculate what the weight is. And so probably if you're trying to figure out what object to isolate, start with the things that mass is given for, you know. That doesn't help you at all when you're actually doing real engineering problems, but in book-type problems, that's something to look for. Okay, so we're going to isolate the mass. And what forces are applied? Gravity, yep. And now we're going to go around the boundary mentally looking for contact. There's one place over here that's a cable. And so the force direction is that way. I'll call that T1. And then over here, force direction is that way, so I'll call that T2. There's no other place where the outside world is contacting the boundary, so we're done. And now before we can write these into Newton's second law, we need to use what we know about the directions to represent these force vectors, the one associated with T1 and the one associated with T2, as force components, vector components. All right, so cable 1. What we want to do is that force applied by cable 1, we want it to be equal to the magnitude that we're calling T1, that's our scalar variable, times a unit vector. And now calculating that unit vector is just like problems we did at the beginning of class today. A vector that's not a unit vector in the direction we want, how would we calculate that? That's right. So take the destination point minus the starting point. So 2, 1 minus 0, 0. And now we just need to make a unit vector that's in that direction. So we'll figure out the length of this vector. 2 squared plus 1. This actually might be the exact same problem we had earlier. The length is square root of 5. And so the unit vector is 2 over root 5, 1 over root 5. And so finally that force vector, F1, is equal to 2t over root 5, and then 1t over root 5. And now we have to calculate the force vector produced by cable 2. I'll call that F2, and that's going to be equal to the tension T2 times this new unit vector. I guess I'll call that U hat. Question?
That's 2T1 over square root 5 and T1 over square root 5.
Yes, that's right. Okay, so U, a vector that's in the direction of the unit vector that we want, is this destination point, negative 2, 1, minus this starting point. So that's negative 2, 1. Then the length of that vector is negative 2 squared plus 1 squared square root, so you get square root of 5 again for the length. And now divide u by the square root of 5, and you get a unit vector that's equal to negative 2 over square root of 5, positive 1 over square root of 5, and so that force F2 is equal to negative 2t over square root of 5, positive t over square root of 5. Any questions about that? So now we've figured out a way to represent the forces. Oh, I wrote those as t's, but they should be. Is that what you were asking me before?
Yeah.
Why I skipped that? And then you were too polite to. Okay, so this should be 2t1 over root 5. This should be t1 over root 5. This one should be negative 2t2 over root 5 and t2 over root 5. And so what we've done now is, instead of just treating these as force vectors that we didn't know anything about, like here's what would have happened if we would have treated these as force vectors that we just didn't know anything about. This would have been like a vector t1x, t1y, and our force vector applied by that cable would have two variables in it. Instead, because we knew the direction, we've represented that force with only one unknown variable. And so it only takes one equation to solve for one unknown variable. It would take twice as many equations to solve for two of them. Okay, so that's the benefit of this. And we wouldn't be able to solve this problem if we didn't do that. All right, so Newton's second law. Any other questions? So Newton's second law, now we can add up all these forces. There's the weight, which is, I tend to use 9.81 for G. If you want to use 9.8, that's fine. But the weight is 0, negative 98.1 newtons, because it has a mass of 10. And then the other two forces are F1. So that's 2t1 over root 5, t1 over root 5, and then F2 is negative 2t2 over root 5 T2 over root 5. And since this object's just hanging there, there's no acceleration, and so these are equal to 0, 0. Okay, so the first equation, we can think of this as two separate equations. The first one says 2t1 over root 5 minus 2t2 over root 5 is equal to 0. And you can move the negative term to the other side, divide by the constants. This tells you that t1 is equal to t2. And then the second equation says, I'll move the 98.1 over to the right side. So we have, and I'm going to substitute in for T2. So I'm not going to do that all at once. Okay, so T1 over square root of 5 plus T1 over square root of 5 is equal to 98.1. And so 2t1 over square root of 5 is equal to 98.1. And so now you can solve for t1, and you get t1 is equal to 109.73 about. And so therefore T2 is also equal to 109.73. One thing to notice about cables is cables can't ever push on things. Cables can only pull. So if you ever set up a problem with a cable and get a negative answer for a tension, something went wrong in your assumption about the direction that it was pulling or something, but you need to go back and figure out what went wrong. Tension values should always come out positive. Okay, let's do one more cable example. Have you seen problems that have to do with pulley advantage before in physics? It's pretty cool how it works. So let's say that there's a system of pulleys like this. And there's a single cable that goes through this whole system of pulleys. And down here, you know, somebody's holding it. These have to be, those are not hovering pulleys, so these have to be connected to the ceiling, these two. The other two are hanging and connected to the thing that's being supported. Okay, so the question is, what's the cable tension that you need to apply to support this mass? So what's the required value of T so that this mass is in equilibrium? So what I'm going to isolate is this. Okay, all of the stuff that's hanging. And so I'll draw a free body diagram. The outline looks something like that. And if you're ever confused about a problem with cables and pulleys and stuff, one thing that you can do that seems to make it a little easier to wrap your head around is include a little bit, anywhere that you're chopping off the cables, include a little stump of that cable with your chosen body. And that force then is just going to be pointing right out of that stump of cable that you've included. So I'm going to include just a little bit of cable at these 4 spots. Okay. So now the force acting down is 100 times 9.81, so 981. This is all one, it's all one cable going through those pulleys. So anywhere that the cable is crossing through the boundary, you know that it's applying that same tension force T at every point. And so you just have a T here, 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 and here. Each one of those is the same value T. Any questions about that?
Is that just because it's given in this problem? Or is it just because of this configuration?
It's the fact that there's 4 of those there. It's just because of this configuration. And so Newton's second law says, we're just going to go through all 5 of these force vectors. We have 0t plus 0t plus 0t plus 0t. Those are all the cable forces. And then we have plus 0, negative 981 is equal to zeros. And so the first equation says 0 is equal to 0. That's a relief. The second equation actually ends up being more useful. It says that 4t is equal to 981. Or in other words, t is equal to 20, I think that's 245.25. So in other words, in this configuration, you could lift up basically 1,000 newtons of weight by applying a 250 newton force to that cable, which, if you haven't seen this before, I think everybody's sort of aware that this is something you can do with cables. But the first time you see this, that sounds impossible, like we must have done something we're not allowed to do or something. But it's not very hard. Remind me in office hours if anyone wants to see it. It's not too hard to rig up pulleys and show that it works like this, Rig up a couple pulleys this way and cut down the amount of force that it takes to hold something up. It's pretty cool how it works. I think there's a problem like this coming up in either today or tomorrow's problem set. anybody have a feel for what would happen if we? Okay, so like, what if you're like, oh, I like everything about this except it takes up too much space up and down. So what I want to do is move the hanging pulleys up so it's almost completely horizontal, and so that cable is just basically going, you know, that cable, say, is at a 30-degree angle. You know what I mean? Anybody have a feel for what that does to this force? Change anything? Well, you do have X components, and your Y components then are just sines of angles. And as that angle gets smaller and smaller, that tension force that's required increases. And you might think that it increases until you're getting no pulley advantage benefit out of it. In fact, it increases towards infinity. Like the closer you get to this thing being horizontal, the bigger that value of T gets, and it's unbounded. So don't try that. if you're trying to improve the performance of that system, that idea of changing the angles or whatever, that was a dumb idea. Any questions about that? All right.
Maybe also like same thing if you're just gonna be talking about angles. If the angle is gonna be almost down,
Mhm.
so all the tension gonna be going down. So
That's where it's maximized. That's where the pulley advantage is maximized. Is if it's all vertical.
I'm talking about just cables, not pulleys. If you just had cables,
Mm-hmm.
no.
I don't know. I can't picture. Okay, we'll talk about it later. So the next thing we need to talk about is a naming convention that's going to be really useful in this class. So this is a convention for naming force vectors. And we haven't talked about couples yet, but it also works for couples. The one thing to keep in mind about this naming convention is don't use it with scalar variables. Don't use it for scalar force variables. You only want to use it for force vectors. So only force vectors, not scalar force variables. And an example of a scalar force variable is like that variable T, the tension variable. So the convention we're going to use says the force sub AB is the force acting on body A by body B. Some people do it the other way. There's no agreement, like overall agreement on which way to do this labeling. So it'd be nice if that was more universal. I'm not totally sure this is true, but my guess is that it's more of a physics thing to, so like in physics, I think it's more common for people to say FAB means the force A applies to B. In engineering, it's more common to say FAB is the force on A by B. But we're going to do it this way, the force on A by B. Okay. One benefit of this is for a single isolated body, all of the forces acting on that body have the same first subscript. You know, like if you're isolating body A, then all the forces around it are FA1, FA6, FAQ, FA, you know, because A refers to the body that you're isolating. Okay, so here's an example. So let's say that you have a 20 kilogram block resting on top of a 50 kilogram block. And those are resting on the ground. And then you have a 50 Newton force pushing to the side on the 20 and a downward force of 100 Newtons pushing on the top. And we're going to assume that all contacts have friction. So let's just draw the free body diagrams of each of these. So draw free body diagrams for the 20 and the 50. Okay, so what forces are acting on the 20? Let's go in the really overly, yeah, right. That's what I'm getting at. So first is the weight, 196.2. And now we're going to go around the boundary looking for contact. There's contact at the top, contact at the side, then there's contact at the bottom. That contact has friction, which means that we're going to do a lot of these, and the way you represent contact with friction is as a fully unknown force vector. Normally, like in physics, you would represent it as a normal force and a friction force that's equal to some coefficient times that normal force. In these kind of problems, static problems, usually we're dealing with static friction, and usually we know that it's at rest, so that approach doesn't help us. Because we don't, you know, using static friction, remember, you can only calculate the maximum friction force that can be applied. You can't calculate the actual friction force. And so for us, we're just going to treat friction contacts like a fully unknown force vector. Okay, so what's the name for this force? That's right. So, no, that's wrong. That's almost right. Opposite. Force on the 20 by the 50. Any questions about that one? So on 20 by 50, on 20 by 50. Say that all the way home in the car. And then the free body diagram for the 50. There's the weight. So that's 490.5. And now going around the boundary, where is there contact between the outside world and this boundary? At the top. And what's the name for that force? That's right, on 50 by 20. Where else? Yep. And so what's the name for that? On the 50 by the floor. And what about that 100 Newton and 50 Newton force. Nope, those are applied to the 20. They're not applied to this boundary, and so those don't appear there. And that can be a little confusing, I think, because you think like, well, all of these forces are affected by the fact that those 50 and 20 are there, so it must appear here somewhere. Well, if we calculated this, we would see that those affect these forces, but they don't affect them directly. They affect them by changing the value of this F5020. Okay, and that changes the value of this F50F. Any questions about that? All right. I'll finish talking about this tomorrow, but the next thing we need to talk about is Newton's third law. I'll abbreviate that N3L. So Newton's third law is the one that says in words something like, for every action there's an equal and opposite reaction. But thinking about it that way can be horribly confusing. So for us, the definition is just this. FAB is equal to negative FBA. So any force vector on body A by body B is just equal and opposite to the force on body B by body A. Since we only use this subscript notation to talk about force vectors, though, when we're dealing with forces with known directions, where the variable is a scalar force variable, so when you have forces with known directions, keep the variable the same. Let me elaborate a little before that. When you're going from the contact force on one body to that same contact force on the other body, keep the scalar variable the same and just switch the direction of the arrow. Keep the scalar variable unchanged. So you don't change the sign on the scalar variable, you just change the direction of the arrow. Okay, so let's do one quick example. So let's say you have a 50 kilogram box and a 30 kilogram box. And 100 Newton force acting here. And let's say that this time we're going to treat this as frictionless, the contact between the boxes and the ground. And we just want to draw free body diagrams of both of these. So free body diagram of the 30 kilogram box. There's the weight, 294.3, I think. Then, since this is a frictionless contact, there's just a normal force. I'll call that N30. The hundreds acting on the left. And now finally there is a force pushing on the 30 by the 50. I'm going to just call that R. And now we'll go to the free body diagram of the 50. (50 times 9.81 is 490.5). There's a normal force N50. There's a contact force with the wall. But the thing that this whole example is designed to show is the force. So there's a contact force between the 30 and the 50. That's represented on the free body diagram for the 30 with this R. So on the 50, we're going to represent that as an arrow going the opposite direction and a variable R. That's how that contact force appears. Any questions about that? Okay, that's it.